This is Module 4, Radiation Dose and Risk in Cone Beam Computed Tomography. At the end of this module, we hope that you will have gained a knowledge of the effective doses associated with cone beam CT and other dental X-ray techniques. We also hope that you will have a basic understanding of how the effective dose of cone beam CT is influenced by equipment and patient-related variables. This will be an introduction to optimization, which will be covered in more detail in a later module. In terms of skills and abilities, we hope that you'll be able to communicate doses and risks of cone beam CT to staff and to patients in an effective way. Finally, in terms of your overall judgment and stance, we aim to achieve an evidence-based understanding of dose and risk associated with cone beam CT that can be communicated to others in easily understood language. In the previous module, we established that the risks from low-level radiation exposure are believed to be stochastic in nature, that is, a chance effect. Most authorities propose that risk is directly related to radiation dose and that there is no threshold. In dental radiology, the risk is of inducing cancer. And for the same X-ray dose, the risk is believed to be higher in children and lower in the elderly. Remember that this is very important because of the high proportion of patients radiographed and scanned in dentistry who are young. So in this module, we want to look at the specific aspects of radiation doses and risks from dental cone beam CT. In cone beam CT, as in all radiology, dose estimation can be quite complicated because we can use many different parameters to reflect the radiation dose. These can be anatomical in nature, such as the absorbed dose to a particular organ, for example skin dose, or we can use effective dose. But we also use technical parameters. We can talk about radiation dose in a very practical, simple way by looking at the current and the exposure time, the MAS in other words. Or we can use more complicated methods that are based on technical measurements, such as the CT dose index or dose area product. But effective dose is the most relevant and comprehensible dose parameter to demonstrate patient risk. So that's what we're going to concentrate on. So let's look at how dose is measured. Essentially, in very simple terms, dose is about the energy imparted to tissues. The unit of energy is the joule, the unit of mass is the kilogram. So we can talk about dose in very simple terms as joules per kilogram. That would be the unit of dose. And in dosimetry, this gives a special name, the gray. So 1 joule per kilogram equals 1 gray. This is called absorbed dose. To complicate things a little, the absorbed dose has to be multiplied by a weighting factor according to the type of radiation being used. This is because different types of radiation can produce different degrees of damage for the same amount of energy imparted. For example, protons and alpha particles have a much higher biological effect than do X-rays. Fortunately for us, the weighting factor for X-rays is 1. So in fact, there's no particular difference numerically. The only difference that we see is that the unit changes from a gray to a sievert. This is called equivalent dose. Effective dose takes into account the fact that different tissues in the body have different radiosensitivities. If we assume that the whole body adds up to 1, a numerical value of 1, then each organ or tissue is allocated a weighting factor, and this table illustrates those weighting factors. When we perform dosimetry, what we need to do is calculate the equivalent dose for each organ or tissue and multiply it by this weighting factor to give us an indication of the biological effect. In the case of a particular type of X-ray examination, we do this for all the relevant organs and tissues, and then we add them up. So we have the sum of all these different factors. But how is this possible to carry out in real people? Clearly, we cannot measure the dose to internal organs in a living patient. And in reality, the answer is we can't do this in real people, and we have to resort to using phantoms, anthropomorphic phantoms, that mimic as closely as possible real patients. Here are some examples of anthropomorphic phantoms. Let's look at these in a little bit more detail. This is a lateral head radiograph of this anthropomorphic phantom. What will be striking is that there is real bone and real teeth in this phantom. Modern phantoms that you would purchase today don't contain real skull material and are replaced by tissue equivalent material. Nonetheless, you'll see that the soft tissues are represented by a rubbery material, and also you'll notice very clearly on these pictures that the head phantom is sliced in an axial plane. Let's look inside a phantom. This is a more modern one, and here the bony material is replaced by tissue equivalent material. What can we see when we look at one of these slices? Well, if you look very carefully, you'll see that there's a grid pattern of tiny little holes distributed all over the phantom surface. This is true for every single slice of the phantom. Those marked in yellow lie in the region which would correspond to part of the brain. The arrow in black is pointing to a hole that's lying within bony representation of tissue. The small holes that you saw in the phantom are filled with thermoluminescent dosimeters, TLDs for short. What are these? Well, they contain materials such as lithium fluoride. This material has a particular property that when it is exposed to radiation, the energy in the radiation is stored and will only be released when the material is heated in a special reader. This gives an indication of the amount of radiation that the dosimeter has received. So when we want to calculate the effective dose from a particular radiological procedure, we assemble many of these small thermoluminescent dosimeters in the phantom, expose the phantom, usually many times in order to get a substantial amount of radiation built up, and then we analyze each individual TLD and work out first the absorbed dose, then the equivalent dose, and then calculate the effective dose for that procedure. Clearly, in vivo, this could only be used for superficial skin doses. But by using the phantoms, we can get a true indication of effective dose. Let's just summarize what happens. We place the TLDs into the phantom, they're X-rayed, and the energy from the X-rays is stored. These are loaded individually into the TLD reader. This is heated, and energy is released as light when they're heated. A photomultiplier tube detects the light, and then this goes to a meter which gives us a readout which reflects the amount of radiation that that individual TLD received. That sounds straightforward, but there are important limitations to studies in the literature related to effective dose. Phantoms are often average adults, and females and children may have different sizes, and therefore the doses that are calculated may not be directly applicable to those individuals. Different manufacturers' types of anthropomorphic phantoms are used. TLDs themselves have some uncertainty on measurement, and calibration is particularly important and may not be the same between different research centres. Finally, where you put the TLDs in the phantom isn't consistent or standardized in any way, and some studies in the literature use too few TLDs, which reduces the likelihood that their measurements are accurate. So it is important to bear in mind the limitations of these studies. Okay, that's the background. Let's look at some actual figures. The figures on the screen here are from the review of effective doses from conventional imaging methods included in the Sydentex Provisional Guideline document published in 2009. Ranges of dose are given because these are taken from several different publications. The unit of dose is the microsievert. That's important to understand that we're dealing here with millionths of sieverts, a fact that represents how big a unit the sievert is. What you'll see is that for intraoral radiography, the dose is less than 8 microsieverts. It's probably much lower than that for modern equipment and materials. Panoramic radiography has quite a wide range, again reflecting different types of X-ray equipment, the field size that's used, and the image receptor that's used. In contrast to these quite low figures, you'll see CT examinations represented here, the sort of CT examinations that are used in dental implant planning. Again, you will see some very big ranges in these figures. But nonetheless, it's easy to see that with CT scanning, this is medical CT scanning, not cone beam CT, we see a quite high dose is feasible when performing this procedure. So this puts things into some kind of perspective when we look at cone beam CT effective doses. This table is taken from the Sydentex Provisional Guideline document. No, I've got to start that again. This table is also taken from the Sydentex Provisional Guideline document published in 2009. As you see, we have listed doses for particular pieces of X-ray equipment in that document. It is important to remember, however, that these particular items of equipment may alter in their performance due to manufacturers' improvements, and you should not, certainly at this stage, consider these accurate doses for these pieces of equipment. You will also see the effective doses are divided into two categories: dentoalveolar CBCT and craniofacial CBCT, depending on the field of view size used for the examination. What is most striking here, perhaps, is the enormous range in doses that have been recorded. Now, while some of this may reflect differences in methodology used by the investigators, it probably also reflects real differences between different items of equipment. This underlines the fact that it is impossible to give one single figure for radiation dose from cone beam CT. Even for individual items of equipment, you will see ranges of dose given in most categories. And these are also quite substantial differences. This reflects different field sizes used, different resolutions, and different locations of the examination being measured. For example, the effective dose from a scan to the anterior maxilla may be completely different to one using exactly the same field size, same exposure factors, performed in the posterior mandible, because different tissues are being X-rayed. What's important to understand is that very exact figures, such as those in the table on the previous slide, give an indication or a suggestion of accuracy that may not actually be valid in real life. Different methods using different phantoms can give different results for the same X-ray examination. So it may be better to use more rounded figures, such as I show here. When we're looking at conventional dental radiography, such as intraoral and panoramic radiography, we're probably, in most cases, working in this kind of range, 1 to 20 microsieverts. At the bottom there, for medical CT, multi-slice CT scanning, we're probably working in the range shown of maybe 200 to 2,000 microsieverts. With cone beam CT, we're somewhere in the middle, but you'll also see an overlap between all three categories. So to make it even more simple, I suggest that maybe we should consider the doses given in cone beam CT to represent, in many cases, about 10 times the sort of range of doses achieved in conventional dental radiography, whereas medical CT scanning may in many cases give a dose about 100 times that received in conventional dental radiography. This is a very simplified way of expressing effective dose to patients undergoing dental cone beam CT and other examinations, but it is probably easier to remember and more useful in real life. In the slide showing the table of doses from dental cone beam CT, it was clear that there is a lot of variation in dose possible depending on the type of equipment, the manufacturer's type of equipment used. So here we'll briefly think about the factors that influence the effective dose in cone beam CT. The first of these is essentially the quantity of X-rays used and also their quality, and by quality we mean the energy in the X-rays. This reflects the kilovoltage, the current and time product of exposure, and also the filtration in the machine. Generally speaking, these things are out with the control of the operator. Your equipment comes with particular filtration and is also equipped with recommended exposure factors and kilovoltage settings. But nonetheless, these factors do significantly influence effective dose. One thing that's apparent to all of us is the influence of the field of view and collimation. All other things being equal, a small volume, such as shown here, achievable with some pieces of CBCT equipment, will give a lower dose than larger volumes, such as seen here. But I emphasize that all other exposure factors would need to be equal for that relationship to be very clear-cut. Another factor that's important is the voxel size of the examination. In other words, the resolution of the examination. Generally speaking, smaller voxel sizes, in other words higher resolution examinations, will be associated with higher doses of radiation, all other factors being equal. Another factor influencing effective dose in cone beam CT is the number of projections used to produce the image dataset. Just to remind you that when we perform a CBCT examination, the dataset is produced by many basis images being produced by the X-ray source and the image detector moving around the patient's head, as shown here. And this would proceed on in most pieces of equipment for a substantial rotation around the patient, perhaps a full rotation in many pieces of equipment. It is possible, of course, to produce images from cone beam CT using fewer basis images. And if this facility is available on items of equipment, this can be used as a way of reducing effective dose. The use of shielding devices has been investigated for cone beam CT, and there is some evidence that using thyroid shielding, such as you see here, will lower the effective dose by preventing or reducing irradiation of the thyroid gland. Finally, the choice of digital detector will also influence the effective dose considerably, and this certainly will contribute to the differences in doses associated with different items of manufacturer's equipment. Nonetheless, this is not something that the operator can control. So, having covered all these factors which can influence the dose given in a cone beam CT examination, it's clear that variations in any one of these parameters will alter the radiation dose. This is complicated by the fact that you may have combinations of variations in these factors. And this may produce some results for effective dose that could feel wrong. For example, having a large field of view may not necessarily give a higher dose than a small field of view, because the resolution of the examination may be lower for the larger field of view. So one factor is tending to increase the effective dose, and another factor will be reducing it. The International Commission of Radiological Protection gives three fundamental principles of radiological protection: justification, optimization, and the application of dose limits. Optimization relates very much to this choice of different parameters in equipment use, and this will be covered in more detail in a subsequent module. Let's move on now and just think a little bit about explaining dose to patients and the public. The European Guidelines on Radiation Protection in Dental Radiology, published in 2004, made a very specific recommendation that informed consent should be obtained from patients prior to radiography in accordance with national requirements. Simple terms, we can only X-ray patients with their consent. And direct questions from patients regarding radiation dose or the need for radiography, the need for cone beam CT scanning, needs direct, truthful answers. The problem is, of course, that explaining factors like dose, risk, units of dose, and so on and so forth can actually be incredibly confusing not only to the patient, but also to some professionals. In practice, we must gauge the information that we give to patients depending on our particular judgment of the patient's capacity to understand. Clearly, there would be a big difference in what we could explain to a child compared with what we might explain to a highly intelligent professor of medical physics. But what we must never do is deny any risk from X-ray exposure if we're challenged by a patient. One way to deal with doses is to try and relate these to annual average background radiation in terms of days or weeks of equivalent radiation exposure. But another approach is to use information sheets such as those that are found in the Sidentex CT website. On the right in the box, you'll see a part of the information sheet that we produced in the Sidentex CT product. What you see here is that we're emphasizing the justification aspects and indeed the optimization aspects in fairly straightforward language. This helps to reassure patients that we're only performing the scan in order to benefit them in terms of the medical and dental treatment they are going to receive. So, in summary, the radiation doses in cone beam CT are typically larger than conventional dental imaging, but smaller than those with medical CT scanning. Doses with cone beam CT are best expressed as ranges rather than absolute values. Many variables relating to equipment can influence the effective dose. producing opportunities for optimization of dose. And patients do have a right to information that allows informed consent to be given. Please ensure that you've read the dose and risk section of the Sedentex CT provisional guideline document. This gives a lot of useful background information. There are many studies on cone beam CT effective dose. A few of these are listed here. If you have access to research papers, then you may like to look at one or more of these to find out how dosimetry has been performed. This is the end of this module, and we'd just like to acknowledge that the research leading to these results has received funding from the European Atomic Energy Community's 7th Framework Programme under the grant agreement of Sedentex CT.